Greetings, calculus fans. Welcome to our next video on the ratio and root test. So in this video, we'll start with a new classification of convergence, and then we'll talk about two new tests for convergence. So here's a new classification for convergence. It's called absolute convergence. A series n equals 1 to infinity of a sub n's. So this could be positive or negative terms, doesn't matter. This series is said to be absolutely convergent if its series of absolute values converges. So the idea here is that the series of absolute value terms is the absolute value of A1 plus the absolute value of A2 and so on. And those are all positive terms. So we have lots of tests for series with positive terms. And if the series of positive terms converges, then we say that the original series is absolutely convergent. So just a couple quick examples to illustrate absolute convergence or not. Here's the first one. This series n equals 1 to infinity of minus 1 to the n minus 1 divided by n squared is absolutely convergent. Okay, and again, to see this, we'll just have a look at the series of positive terms. And here we see that the series of absolute values is a p-series with p equals 2. It's convergent, so we say that the original series is absolutely convergent. On the other hand, the alternating harmonic series that we looked at last time is not absolutely convergent. So to see this again, we'll just have a look at the series of absolute value terms. So that series of absolute value terms, of course, gives us the harmonic series, and we know that the harmonic series is divergent. Now, on the other hand, we've seen that the alternating harmonic series is convergent. So this gives us a second new classification called conditionally convergent. A series is conditionally convergent if it converges, but not absolutely. So the alternating harmonic series is a perfectly good example of conditional convergence. Okay, so again, the alternating harmonic series is convergent but not absolutely convergent, so we say that it is conditionally convergent. Now, this idea of absolute convergence can be used on other series too. It often ends up being a convenient way to test a series for convergence, that a series that has positive and negative terms but it's not alternating. So this series is an example of a series with positive and negative terms that's not an alternating series. So in order to test this for convergence, we'll first have a look at the series of absolute values. So we'll start with the observation that the absolute value of sine 4n over 4 to the n is less than or equal to 1 over 4 to the n, because sine in absolute value is always less than or equal to 1. Now, a series with terms that look like 1 over 4 to the n is a convergent series because it's geometric. Now, by a comparison test, the series of absolute values is less than or equal to the convergent geometric series, so it also converges. So since the series of absolute values converges, the original series is said to be absolutely convergent. Okay, go ahead and change gears here and talk about two new tests. First, the ratio test. The ratio test is a test for convergence, and it begins by looking at the limit as n goes to infinity of the absolute value of consecutive terms in a series. So to apply the ratio test, the first thing you do is have a look at this limit and get some number. Of course, that's a positive number, right? Because you're looking at a limit of positive things. And if that number is less than 1, then the series is absolutely convergent. If that number is bigger than 1, then the series is divergent. And if that number is equal to 1, then we don't know anything new. The series could be convergent or divergent. So a couple pro tips for using the ratio test. The ratio test is especially good for factorials and powers of n. we'll make lots of computations that make use of the fact that n plus 1 factorial is the same as n plus 1 times n factorial. And similarly, that x to the n plus 1 is the same as x times x to the n. It turns out that the ratio test is bad for series where the limit comparison test or comparison test might apply. Usually in those cases, you'll end up getting 1 for the L, so the ratio test is inconclusive. Okay, so a few examples illustrating use of the ratio test. Here's the first one, test the following series convergence. So we'll go ahead and apply the ratio test. Okay, so we'll go ahead and look at the limit as n goes to infinity of the absolute value of consecutive terms in the series. This ends up being the limit as n goes to infinity of the quotient of n plus 1 over 5 to the n plus 1 divided by n over 5 to the n. And here I've just removed the absolute values because everything is positive. Invert and multiply the denominator. And now we'll go ahead and make use of the fact that 5 to the n plus 1 is 5 to the n times 5. So we end up with an expression that looks like the limit as n goes to infinity of 1/5 times 5 to the n, 1/5 times n plus 1 over n. And of course, as n goes to infinity, n plus 1 over n goes to 1, and we're left with a limit of 1/5. So this is the L from the ratio test. Our L is between 0 and 1, so the series is absolutely convergent. Okay, another example illustrating use of the ratio test. Let's have a look at the series sum n equals 1 to infinity of n factorial divided by 3 to the n. So again, we'll start off by applying the ratio test. So we apply the ratio test, which has a look at the limit as n goes to infinity of the absolute value of consecutive terms in the series, a sub n plus 1 over a sub n. Simplify, simplify, simplify. Recognize that n plus 1 factorial is the same as n plus 1 times n factorial, and that 3 to the n plus 1 is the same as 3 times 3 to the n. Of course, these terms cancel, and these terms do too, and we end up with the limit as n goes to infinity of n plus 1 over 3. Now, of course, this limit is infinity. The limit as n goes to infinity of n plus 1 over 3 is infinity. So in this case, the result of the ratio test yields a number that's greater than 1. Therefore, the ratio tells us that this series diverges. Okay, super. Just one more example illustrating the use of the ratio test. Here's the last example. Let's test the following series for convergence. The series n equals 1 to infinity of n to the n power divided by n factorial. So again, when you see factorials and powers of n, think ratio test. In this case, we'll have a look at the limit as n goes to infinity, again, of the absolute value of the ratio of consecutive terms in the sequence or in the series. So have a look at that limit. Simplify, simplify, simplify. Recognize that n plus 1 to the power n plus 1 can be reduced, that n plus 1 factorial can be reduced, that terms cancel, and more terms cancel, and ultimately you're left with the limit as n goes to infinity of something all to the n power. Now, this expression, n plus 1 over n all raised to the n power, you can think of as 1 plus 1 over n all to the n power. And it turns out that that limit is a special limit that we know from Calc 2. So this special limit from Calc 2, limit as n goes to infinity of n plus 1 plus 1 over n all to the n power is e. Of course, e is a number that is greater than 1. So by the ratio test, this series is divergent. Okay, one last test for convergence called the root test. So state the root test. It's sort of similar to the ratio test, and then just do one quick example. So the root test has a look at the limit as n goes to infinity of the nth root of the absolute value of a sub n. And again, if that limit is between 0 and 1, then the series is absolutely convergent. If that limit is 1, then the series is divergent. And if that limit is, if the limit is greater than 1, the series is divergent. And if the limit is 1, then the root test is inconclusive. Okay, so the root test, as it turns out, is good for limits involving powers of n. So here's an example using the root test. Let's go ahead and have a look at the following series. So we'll apply the root test, having a look at the nth root of the absolute value of the nth term in the series as n goes to infinity. So in this case, the root test, the nth root of that n power just kills off the power. We're left with the limit as n goes to infinity of n squared plus 1 over 2n squared plus 1. And using the ratio of leading coefficients, we know that this is 1/2. Of course, 1/2 is a number that's between 0 and 1. So by the root test, this series is absolutely convergent. Okay, thanks folks for your attention. Hope you've enjoyed this video on absolute convergence and the ratio and root tests. Have a great day, and we'll see you next time. Bye-bye.